In this lesson, we'll discuss the relationship between the voltage, the current, and the charge for a capacitor. Before doing so, though, we want to refresh our memory talking about the relationship between voltage and current in a resistor. I represented the resistor here on the left. That's the schematic symbol. I represented the voltage in red and the current in green. And down here, I've wrote the equation, the relationship between voltage and current for a resistor. This is called Ohm's law, and is a representation of a very simple relationship. It's a linear relationship where the current through the resistor is simply equal to the voltage divided by the resistance. And you can also obviously write this equation in many different ways. For example, you can write it like this: V equal to resistance multiplied by the current, and vice versa. Now, what we want to do now is to represent this relationship in a chart. This is a VI chart. The VI chart represents a VI curve, which is the voltage and current relationship of a component, in this case a resistor. So as you can see, a linear relationship is simply represented by a straight line. I wanted to highlight a few different things. So first of all, as clear from the equation, when the voltage is zero, the current will be zero. So all of these curves are passing from the origin of the graph. And that is always the case with the resistor. And then another thing that is interesting to highlight is that in this case I represented curves for three different resistors. And you can see that as the resistance becomes larger, the slope of the curve becomes lower and lower because you need a higher amount of voltage to generate the same current. In fact, if I clean up a little bit here, and let's say I assume, let's pick a certain value for the current, Ix here, for example, and I draw a line. So that is a line that represents the value of current equal to Ix. You see that for resistor R1, that is the smallest of all, you only need this amount of voltage to generate that current. For R2, you need a higher amount of voltage. And for R3, which is the bigger resistance, you need an amount of voltage that is even higher to generate the current Ix. For the most mathematical view, you can also note that there is a relationship between the slope of the curve and the equation, because the Ohm's law, it's just a linear equation. So the V in this case is the independent variable, which is the horizontal axis. The current is the output of the equation in this case. And you can see that usually a straight line is represented with an equation that is mx plus q, where m is the slope and q is like a fixed constant. So in our case, the q is 0 because the current is going to be 0 when the voltage is 0. But our m in this case, which is a representation of the slope, is 1 over r. So each of these curves have a slope that is equal to 1 over r1, and this one has a slope that is equal to 1 over r2, and the last one has a slope that is 1 over r3. So the larger is the resistance, the lower will be the slope of the curve. Let's talk about the capacitor now. Just as I did for the resistor, I represented a schematic symbol of a capacitor. I indicated the voltage in red, the current in green. This time I also indicated the charge in blue, which is an important parameter for capacitors. Down here I also wrote the equation between the charge stored in a capacitor, the capacitance, and the voltage. This equation is a linear equation. So similarly to what we've seen for the resistor, for Ohm's law, this will be represented by a straight line passing from the origin. And now this is an equation representing a completely different thing. It's not a VI curve, but it's still mathematically a linear equation, so it's still represented by a line. Similarly, as we've seen before, different value of capacitance will give you a line with a different slope. And in this case, the higher is the capacitance, the higher will be the slope, because for the same voltage, if the capacitance is higher, that means you have stored a larger amount of charge. The relationship between the current and the voltage in a capacitor is not as simple as in the case of the resistor, where you have a linear relationship. So we wanna discover it going step by step, and we're gonna go with a little exercise where I provide a value for the current, a waveform for the current, and we extract the equivalent value for the charge and then for the voltage. So here I have a graph that represents the behavior of the current over time, and then down here we have a graph that represents the behavior of the charge over time, and will also represent the voltage. One thing that I want to highlight is that the behavior of the current was an input of this exercise. So the shape that I chose was completely arbitrary for the current, and I chose this specific shape because it will let me explain a little bit better how the capacitor works, but it could have been any shape for the current because it was our input. Whereas the charge and then the voltage will be just like an output, a consequence of the waveform of the current. Now, as you can see, the current waveform is split in 5 different regions where the current behaves in a completely different way, as you can see here. So in the first region, we have a constant current that is pretty high, a constant and positive current pretty high. Then in the second region, we have a constant and positive current, but the value is rather low. In the third period, we have zero current. In the fourth period, we have a negative, small current going through the capacitor. And in the fifth period, the current is positive and it's increasing linearly with the time. So the current is getting higher and higher as the times go. The next step is to take the graph showing the waveform of the current, and by using what we know about the capacitor, extract the behavior for the charge. As you can see, I already done that, and we're going to describe each of the periods in details. But in order to understand how I went from the current to the charge, we need to remind ourselves what's the definition of the current, and also to resort once more to the hydraulic equivalent of a capacitor. So the current, as we've seen, is defined by the delta charge over delta T, and in our hydraulic example is represented by the flux of water, which is represented as, for example, cubic meter of water per second. Now the capacitor can be represented as a tank with a certain amount of water inside, and the volume of the tank is the representation of the capacitance, while the height of the water, the level of the water, is a representation of the charge. This relationship, this hydraulic example, should allow us to get the behavior of the charge, at least qualitatively, for a given behavior, for a given waveform of the current. If you take the relationship, the equation representing the definition of the current, and you multiply both sides by delta T, what you get is that delta Q is the current multiplied by delta T. This equation is telling you that there is a linear relationship between the charge and the time if the current is constant. This is pretty intuitive if you think about the hydraulic example, because this simply means that if you have a constant current, which means a constant flux of water going into your tank, the level of the water will just increase linearly with the time. So it will just go up like a straight line, and if you, for example, wait twice as much time, your level is going to increase twice as much the amount. So let's see, we'll use this relationship to solve the behavior of the charge for the first 4 periods. So let's start here. So first of all, I'm assuming that the charge starts from 0. Again, this is an assumption that I made. It's totally arbitrary. The charge and the capacitor could have had any value at the beginning. It's a state of a system, but let's make things simpler and assume the capacitor is discharged at first. So the voltage is 0, the charge is 0. Now, in the first period, we have a constant current, so we can use the relationship up there, and it's pretty high. So as I said before, that means that you have a stream of water, a flow of water going into your tank. It's pretty consistent amount of water. It's positive, so the water is going into the tank. That means that the charge is increasing linearly with the time. So we go from here to there, and then we go in a linear fashion. You probably understood the trick now. In the second period, the amount of the flow of water has decreased. It's still positive, but it's much lower. So now the charge, the level of the water will keep increase to the next level, still linearly, but at a much lower slope. So I want to highlight that this equation in effect gives you the delta Q. So it doesn't give you the total charge, it doesn't give you the total level of the water, but for each of the period will give you the additional change from the initial state of the level. There can be a positive or negative change, but it's simply the change. So you always build on top of whatever was the leftover charge that you had in the previous period. Now in the third period, the current is zero. So current is zero means that we turn off the water. So unless your tank has leaks, that means that the level of the water will stay the same, hence the level of the charge will stay the same. And finally, in the fourth period, the current is small, but it's negative now, which means that we are taking the water out of the tank somehow at a constant rate. So that means that the level is decreasing at a constant pace, so just as a straight line, and it will settle to a certain new level at the end of the period. It's a little bit more difficult to determine the behavior of the charge during the fifth period, because in the fifth period the current is not fixed, but it's changing. However, we can use the learnings that we had from the first four periods, and we can apply it there to get a qualitative waveform for the charge as well. So I believe that if we have to summarize really in few bullets what we learned with the beginning of the exercise, we really learned two things. So one is that whether the charge increase or decrease, it really depends on the sign of the current. So when the current is positive, the charge is increasing, and when the current is negative, the charge is decreasing. So in the fifth period, despite the fact that the behavior of the current is kind of strange, it is always positive, so we expect the charge to increase. The second thing we'll learn is that the pace, the speed at which the charge is increasing in a period depends on the magnitude of the current. Here we see that the current is changing with time, but what we can do is that we can look at few points along the curve and determine what we expect to see, and based on that we can draw a waveform for the charge. So if you look at the beginning of the curve, we see that the current is positive, so the charge has to increase, but the current is pretty low. So we expect that in this region the charge will increase, but slowly. If you look at the end of the curve, at the end of the period, the fifth period, we see that now the current is still positive, but it's much higher value. So we expect the charge to be increasing pretty fast. It is possible to draw a curve that looks like this, and as you can see, it's a curve that it shows that the charge is growing, and the speed at which the charge is growing is becoming faster and faster with the time. If you're curious, it's possible to mathematically calculate that the behavior of the charge in the fifth period is proportional, this symbol means proportional, with the square of the time, which means that differently from the other periods, where if you double the amount of time with the current, you will end up with twice as much extra charge. In this case, if you double the time of period number 5, the delta charge that you obtain is not 2x, but it's 4x. I want to now make an important point regarding to the state of a charge of a capacitor, and it is something similar to what I said at the beginning when I said that assuming that the charge at the beginning was 0 was a totally arbitrary thing, and I could have chosen any other value. That is true. And if you look at the charge evolution on the capacitor, you can notice one interesting thing. In a way, the charge in the capacitor is a sort of a memory effect that the capacitor has on anything that happened previously to that point. So, for example, the fact that the charge is at this level at the end of period 3, it's because the charge started at 0 at the beginning, and then we had a certain amount of current in period 1, a certain amount of current in period 2, and another amount of current in period 3. So in a way, if the exercise started at point 3, we would have a different starting point for the charge, and the reason for that will be completely unknown to us, but it will be a representation of certain values that the current had previously to that point. For instance, if we add a different amount of charge at this point, time equal to 0, we will not know why the charge was at this point. Probably a certain amount of positive current was applied to the capacitor. Doesn't matter, but that value for the charge is an indication of things that happened to the capacitor in the past. And now, if we had to represent the evolution of the charge from that point, it would be very simple to calculate, because as we said before, we are simply computing period per period the extra charge that is added to the capacitor. So in this case, if we start from this point, the resulting charge will be like this. So it will just be exactly the same graph but it will just be shifted up by the amount of the initial charge. Finally, let's calculate the behavior, the waveform of the voltage given the charge. That should be pretty easy because, as we can see here, the charge and the voltage are connected by a linear relationship where the voltage is equal to the charge divided by the capacitance. So if we assume that the capacitance is equal to 1 farad, which is a huge value but makes my calculation simpler, and we also assume, another assumption we can make, that we have the axis of the voltage here is determined such as where you have 1 volt, you have 1 coulomb, so they are aligned. Well, then in that case, the waveform of the voltage will be exactly the same as the one of the charge in this graph. So it will follow exactly the same behavior. Naturally, the voltage is represented relative to a different vertical axis, but I trick the numbers so that they will perfectly overlap. But anyway, the main concept here is that once you have the shape for the waveform of the charge, the behavior of the charge over time, the behavior of the voltage will be exactly the same. So where the charge is increasing linearly, the voltage will also increase linearly, and vice versa. So in a way, when we look at the previous, at the hydraulic example here, the level of the water is a representation of the charge, but it's also it can be also used as a representation of the voltage because there is a linear relationship between charge and voltage for a capacitor. In this lesson, we're going to do a little bit of mathematics to derive the final equation linking the voltage and the current in a capacitor. We have the symbol of a capacitor here where I indicate the voltage and current in the usual way. We remember this equation here that says that the charge on the capacitor is equal to the capacitance multiplied by the voltage. So there is a direct relationship between charge and voltage. And we also know that the charge does not have a direct relationship with the current, but rather the charge is at a certain time in the capacitor is a representation of the values, an indication of the values that the current had in the past for the capacitor, because it is the leftover charge that was left in the capacitor due to certain profile of the current in the past. So in a way, the charge is sort of a memory effect that the capacitor has. We're now going to go and look at the equations that we know for the charge and the current, combine them together to get the final relationship between current and voltage for a capacitor. So we start with the usual equation here, Q equals C by V. And then the other equation here is the one representing the definition of the current. So the current is a delta Q over delta T, which means, again, you always have to imagine that you're sitting by and looking out to, you're the little person and looking at the section of the wire. And this section, you see a certain amount of charge moving down during a certain amount of time. You divide these two quantities, and what you get is the average current during that time. Now, what we're going to do is that we're going to take these two equations and combine it together. So in practice, what we do is that we take the current equation and we replace the Q in that equation with the definition of the Q provided by the first equation. So instead of having that the current is equal to delta Q over delta T, we have that the current is equal to delta C multiplied by V divided delta T. So we just replace the Q with C by V. At first order, the capacitance is a constant value. It's just as we said before, is a property of the geometry of the capacitor and the properties of the dielectric material, so it's not something that's going to change. So we can take it out of the delta operator, and we get that the current is equal to the capacitance multiplied by delta V over delta T, which is the variation of a voltage over a certain time. In order to get to the final mathematical definition, mathematical equation linking current and voltage for a capacitor, we need to go an extra further step and introduce the concept of derivative. What we want to change is that we don't really like the fact that we are expressing variation of quantities using the delta operator, the little triangle. So the delta operator is an indication of a macroscopic change of a variable, like a variable going from 1 to 2, like a kind of a big change. So that is fine for a delta V or delta Q up here, but it's not really fine to be used for delta T. And I'm going to give you an example to explain you why. So let's say you have your charge as you're doing this experiment, being the little guy looking at the wire. you have a charge changing with the time, kind of like that, right? And now I ask you, okay, give me what is the current here. So this is the profile of the charge, right? So that means that every little instant of the time, that's the amount of charge that you see passing, right? So let's say I tell you, okay, give me the current, and you see the definition of the current is delta Q over delta T. So you get to pick your delta T. You can pick any value you want, and that is totally fine. What you'll get will be the average current during that period. So let's say you pick a period that is from 0 to this point. As you look at the charge, you're gonna add it up. So in the end, the value of the charge that you have, the delta Q that you have, it's gonna be pretty much represented by the area under this curve. And now, once you have the area, you're gonna do the ratio with the delta T and you get the current. So if you have to give me the graph of the current over time, now you only have one number for the whole period, and your representation will be sort of a kind of a straight line like this, because you can only give me the average of the current in the whole period, because eventually you come out with just one number, right? If instead of that time period, you chose something that is, let's say, the delta T is like 1/3 than the initial delta T. So this is the delta T that you pick in that equation. Well, then in that case, you will give me 3 numbers, because for each of the delta T you have a different amount of charge. So you have 3 numbers for the current. So you're representing the current during that period with 3 points instead of 1. So it's natural to see how that will be a better representation of the current, right? So you will give me something like this for this part, something like this for the second period, and something like this for the third period. So this is a much better representation of the behavior of the current. You see where I'm going, right? The smaller is the delta T you pick, the better is the representation of the current. So ideally, if you choose a delta T that is infinitesimally small, not exactly 0, but trending to 0, then you will get a representation of the current that is exactly the representation of the charge over time. Choosing something that trends to 0 might seem a little bit complicated, but all I'm saying is that you have to choose a value that is smaller than the minimum unit of measurements of the time that you use in your experiment. So for example, if you are considering an experiment where the minimum information you want to have is in the range of 1 second, then if you choose the delta T to be 1/10 of a second, that is small enough. It can be considered sort of like trending to 0, right? It's kind of like saying, well, I'm measuring the distance from here to another city, so I'm going to use kilometers. The millimeter in that case is pretty much a distance equal to 0, right? Because it's so small, it's so insignificant relative to the unit of measurement that you're using, right? So here is the same story. So mathematically, that is really a number that tends to 0. Really, mathematically, it's like the smallest possible number you can get. But practically speaking, all I'm saying is that you just want to pick this value to be small enough. If you do that, your equation still looks very, very similar. You just change the shape of the operator. So instead of having the operator with a little triangle, which is delta, you replace it with a d, with a lowercase d. And when you write dv over dt, this is called derivative. And if you check it out online, you will see that the derivative, in this case, dv on dt, is a representation of the slope of the voltage over time. So if you have a voltage that over time is being flat, there's no slope, so the derivative is gonna be equal to 0, which means the current of the capacitor will be 0. If you think this makes sense, because if the voltage isn't changing on the capacitor, that means no extra charge is being taken or added to the capacitor, so that means there is no current, right? So it makes sense. If you have the voltage that is increasing like this, then the derivative will be positive, meaning that the current is positive, you have damping charge in the capacitor. If you have the voltage that behaves like this, then the derivative will be positive and even higher value. And if the voltage is doing like this, then you have a negative value for the derivative, hence a negative value for the current, meaning that you are actually taking charge out of the capacitor. What we want to do now is the sort of the opposite exercise of what we've done before. Before we had taken the evolution of the current through a capacitor, and from that, using the hydraulic equivalent of the capacitor, we calculated the evolution of the charge in the capacitor as represented by the level of the water into a tank. And then because we knew that the charge and the voltage are directly related through the value of the capacitance, we got the value of the voltage at the end. Now we want to do the opposite. we start with the behavior of the voltage in the capacitor over time, the evolution of the voltage of the capacitor, and we want to derive the behavior of the current. Now, this is more difficult than the other way around, because going from the current to the voltage, you can use the hydraulic example, which is quite intuitive. Whereas going from the voltage to the current, it's a little bit more complicated. You can still rely on the hydraulic example, but mostly I wanted to derive the equation linking the voltage and the current on the capacitor, and now we can use it much more easily to derive the behavior of the voltage. Now let's start with the exercise. So first of all, again, we start from a certain known value. This is a value that is representative of a charge accumulated in the capacitor up to that point, from the beginning of time up to time equal to 0. We'll just take it as an input. And now we look at the behavior of the voltage to determining the behavior of the current. In the first period, we have 5 periods here. So maybe I'm just going to add the little numbers here. So it's 1, 2, 3, 4, and 5. So in the first period, the voltage is flat. So the voltage isn't changing. So as we've seen before, the derivative, the slope of the voltage would be 0 in this case. Hence, the current would be 0. Okay. And again, this makes sense. It means that the level of the water in the tank of the capacitor isn't changing, which must mean that there's no current going in and out. In the second case, second period, we have that the voltage is increasing. So it's increasing with a constant pace. So the derivative of that will be a positive number. So the current will be positive and constant because the slope is fixed. In the third period, we see that the voltage is decreasing, and you can tell it's decreasing faster than it was increasing before. So the derivative will be negative, and it will give us an absolute value bigger than the one we got in period 2. So that means that the current is going to be negative with a bigger value there. The passage between period 3 and period 4 is a little bit tricky. As you can see, there is a little bit of a discontinuity. You see that the voltage is pretty much stepping from one value to another. If you stick to the mathematics, the derivative of that point is infinite, because you're going with an infinite speed from one point to another. So that means that the current in that point will be shooting up really high. Theoretically, this value will be equal to infinite. Before thinking too much about this, we will revisit this later. Let's move on to the fourth and the fifth period, and I will talk about the consequences and the meaning of this infinite current. In the fourth period, again, the derivative of the voltage is positive and quite low, so it's almost flat. So that means that somehow the current goes down from the infinite, and now it will be flat and a pretty low value. And finally, in the fifth period, we have again the voltage that is flat, that is, the derivative is equal to 0. So the current will be back to 0 again. Let's try to understand this peak of the current that we have derived from the equation. Well, there is two ways to explain that. So one is to just point to the equation. If the equation is correct, technically that point has to have a very, very high current. The equation isn't correct, so the current technically needs to be infinite. Now, let's try to give a more intuitive understanding there, and in order to do so, we can connect to the concept of energy. We remember that a capacitor is an energy storage device, and the energy that is stored by a capacitor, the fact that there is some energy stored, is indicated by the voltage. If you remember, the energy is actually connected to the square of the voltage. So if you change the voltage instantaneously, like this, that means that you are changing the energy instantaneously. Now, we also remember that power is an indication of the variation of the energy over time. So power is, if you want, delta U, if you use U for energy, over delta time. What we are saying is that we had a certain amount of energy change, so this delta U is quantifiable, is a certain number, but the delta T over which delta U happened was pretty much 0. So if you divide a number by 0, then you get P equal to infinite. So that means that in order to allow a change of the voltage so fast, you need an infinite amount of power. Power in the capacitor will be the current multiplied by the voltage, as we've seen before. And the voltage is going from one value to another. So this value could be any number. So it could be going from 1 volt to 2, for example, right? So in order to make the power infinite, because the power is the product of V per I multiplied by I, you'll have to have infinite current. And that is exactly what happens. So in a way, if you want to have an instantaneous change of energy, that is like just a fundamental physical things, you need an infinite amount of power. For a capacitor, that means an infinite amount of current. Capacitors in general are components that oppose to the change of voltage. That means that you can change the voltage across the capacitor, but in order to do that, you have to pay for it. And the way you pay for it is through current. So you want to change the voltage on the capacitor really fast? Very well. Be ready to provide an infinite amount of current. If you want to change the voltage on the capacitor slowly, then you'll have to pay in current, but the tax that you pay in this case will be lower. Like here, for example, we are changing the voltage slowly, so what I have to provide is a current that is just a normal value. I wanted to state the obvious here, because in order to change the voltage on the capacitor, like the way we've shown, instantaneously from one value to another, you need an infinite amount of current. And because an infinite amount of current is not available in any real system, the conclusion is that you can change the voltage on the capacitor infinitely fast. So you're always limited with a certain slope. Capacitors are indeed devices that oppose to the change of voltage, or better, the change of energy that they store. And that makes them ideal candidate in certain type of application that we are gonna see later in the course. In the previous lesson, we've seen that the relationship between the current and the voltage in a capacitor is the following. So the current is equal to C multiplied by the derivative of the voltage on the capacitor. This is bad news because this is a differential equation. So if you want to solve a circuit, even the simplest circuit with a capacitor, you have to solve a differential equation, which is not as simple as if you just had resistor. Here we're going to solve a very simple circuit, and the reality of the practical work, also of an engineer, usually you don't end up solving your differential equations, but what you do is that you study, at least in school, very well 2-3 typical scenarios, and then when you see a complicated circuit, you recognize which kind of category that circuit is, which scenario the circuit follow, and then you know what is the equation, the solution to the differential equation, and you just use it. So the solution will be 100% accurate. You'll not be doing any approximation, but simply you don't need to solve the differential equation every time. Other time, the circuit might be complicated to solve, so you are just going to do an approximation of the circuit, consider the circuit behaves like these are the type of circuit, and then use the corresponding solution. And finally, if the circuit is really very complicated, you're just gonna use a simulator. We're gonna look at here a very classical circuit, which is the RC circuit. So this is a circuit where there is a capacitor and a resistor, and the capacitor gets charge or discharge through the resistor. So as you can see here, I'm already indicating, forget about the value of the current for now, but I'm already indicating that the capacitor starts with 0 voltage. Then we have a supply that is 10 volt that's going to be connected to it through a switch. And you know, probably your intuition already tell you that if you let enough time pass, at the end of the process, the capacitor will be charged to 10 volt. So we are changing the capacitor through a resistor R. So we actually add values of resistor and capacitor. We have a 1 kilo ohm for the resistor and 10 microfarad for the capacitor, so that we can solve the circuit using actual numbers. As you can see, this is the first slide. We are considering the time, what's happening at time 0. And then as we go ahead, we'll move the time ahead step by step with small steps, so that we can solve the circuit in each of these points. So this to avoid having to use the differential equation. Instead of using the differential equation, we will use some more basic relationship and things we know about a capacitor. And the first one you can see here is simply that we know that the current is equal to charge over time. So if you multiply the current by a certain time, you're gonna get a certain delta charge. So at every time we look at the starting point of the circuit and we say, well, there is a certain current going through it for how long we are considering, and then we say, well, that means there is an additional extra charge in the capacitor. Now we know from the relationship of the capacitor with the charge and the voltage that if we have an extra charge in the capacitor, then we're going to have an extra voltage. And I want to highlight the extra voltage, meaning that whatever is the extra voltage that we calculate, this delta V, it's going to be added to the voltage of the capacitor to give us a new voltage that I'm going to call VC first. I'm using this little mathematical notation here first. Same story for the current. So once you have calculated the new value for the voltage of the capacitor, it's pretty simple to calculate what is the current going through the resistor by using the Kirchhoff law of voltage. If you know that you have 10 volts across the supply, now you know what is the voltage across your capacitor, which is this new VC first. And it's very easy to see that the voltage on the resistor will be the difference between the voltage of the capacitor, the voltage of the battery and the capacitor. And of course, once you know that, you just divide by the value of the resistance and you get the current. The switch in this image I'm showing it's open, but for every other case on in the circuit will be closed. So as a matter of fact, you can consider as the switch isn't even there. This might seem a little bit complicated, but don't worry, and we're gonna go step by step every time. Alright, let's start looking at this circuit. At time, let's look for now at the time t equal to 0. Until the switch is open, the current has to be 0, right? There cannot be any current. And for the voltage of the capacitor, by just an arbitrary choice, let's assume the voltage of the capacitor is 0 at the beginning. So voltage of the capacitor is 0. Let's see what happens at time 0 plus. Sometimes people indicate 0 plus, meaning that it's basically 0, but just like 1 nanosecond after it. And the difference between time 0 and time 0 plus is that the switch is closed. So the moment in which the switch is closed, we know already from before that the value of the current of the voltage in the capacitor cannot change instantaneously, because in order to do so, you will have to have infinite amount of current, because the voltage on the capacitor represents energy, so you'll have to have an infinite power to make it change the step function. So if the time that passes from 0 and 0 plus is really short, we can say that the voltage across the capacitor is probably still about 0. Maybe it's not exactly 0, maybe it's like 0.00001 volt, but as a matter of fact, as far as we're concerned, it's 0 volt. So now that allows us to calculate the current in the resistor. So we know that the voltage here is 10. We know that the voltage in the capacitor is 0. If you consider the voltage on the resistor like this, it's very simple to see that the voltage falling on the resistor in this case is 0 volt. You can very simply calculate it doing the Kirchhoff law of the voltage. And in this case, if you have 10 volts, then you divide it by 1 kilo. It's very simple to see that the initial value of the current as soon as the switch is closed is 10 milliamp. So the first point, we solve the first point of the circuit as the time 0 plus, which is voltage of the capacitor is 0 and current in the resistor is 10 milliamp. Let's continue the analysis of the circuit and let's see what happens when we get to the time 5 milliseconds. Now here everything is already solved, but I'm going to guide you through it. So before we said that the current was equal to 10 milliamp at time 0. Now we simply go through this equation one by one, because as you can see, the result of this equation is to give us the new value for the voltage and the current. The first says that the delta charge is equal to, so the additional charge in the capacitor will be equal to the current multiplied by the time. If you substitute here and you take 10 milliamp and this one is 5 milliseconds, because we went from 0 to 5 milliseconds, the results that you get is 50 microcoulomb. Now you take 50 microcoulomb and you divide by the value of the capacitance, which is 10 microfarad, and you get 5 volt. So 5 volt is the difference, the additional voltage in the capacitor. The capacitor has 0 volt at first, so now we're adding 5, so the new value of the voltage of the capacitor is 5 volts. And finally, we use the same equation as before. The current in the resistor will be equal to 10 minus, this time this is 5, divided by 1K, this is 1K, so you get 5 milliamp. So now what we're doing is that we have this here is where the 5 millisecond would be, and what we're doing is that we're indicating that the voltage went from 0 to 5 volt, and the current went from 10 milliamp to 5 milliamp, so it decreased. Of course, the switch is always closed here, don't get fooled, even though I showed it open, but it's closed. And from now on, it will always be closed. Obviously, we don't know what happens, for example, at 3 milliseconds. We just didn't look at that point, so we just went straight from 0 to 5. So I've chosen this time step so that we can see what is the behavior of the voltage and the current. But of course, it's easy to imagine that probably the behavior of the voltage and the current wasn't to go straight, like with a straight line from one point to another. It will be slightly different. We'll see that at the end. But for now, because we don't know anything about what happened between 0 and 5, we only have the point at 0 and the point at 5. We just connect them with straight lines. Now let's look at 10 milliseconds. So same story as before. Remember that the previous value for the current was 5 milliamp. So now we put 5 milliamp here. The time now, it's again actually 5 milliseconds, so the delta time is always the same. But now 5 by 5 is 25, so we have 25 microcoulomb. So you see, same step in the time domain, so we went 5 milliseconds long, but this time the amount of charge that was dumped in the capacitor is actually half the amount of charge we had before. So with 25 microcoulomb, the delta voltage is 2.5 volts now. Now the new voltage of the capacitor is 5 plus 2.5, so 7.5 volts. And finally, the current going in the resistor, hence going in the capacitor, is 10 minus 7.5 divided, so that gives us 2.5 volts, divided by 1K is 2.5 milliamp. So again, as we've done before, at the 10 millisecond mark, we just indicate the voltage. So it looks like the voltage keeps increasing, probably towards 10 volts, as we'll see, and the current keeps decreasing. So it was 10, now it's 5, and now it's 2.5. It's actually halving every time in this case. T equal to 15 milliseconds, so we keep going ahead, 5 milliseconds every time. Same, works before, so we had the current was equal to 2.5 milliamp in this case. We still multiply by 5, so now we get 12.5 microcoulomb. That means the voltage, the additional voltage in the capacitor is 1.25, and now we are summing 7.5 plus 1.25, and we get 8.75. And finally, the voltage across the resistor now is 1.25 volts, and divided by 1 kilo, it gives us 1.25 milliamp. So we keep drawing, we keep connecting with straight line. This is the mark for the 15 millisecond, and we get the voltage again keeps going up toward 10 volts, and the current keeps decreasing. And you can notice that although again we are simplifying things, we're just looking at a few discrete points in the time domain, you can tell that the slope, the speed at which the voltage increase and the current decrease is slowly and slowly decreasing. We could keep going ahead, try to solve this circuit step by step, and for example go ahead and look at 20 milliseconds. But I think you got the gist of it, so it's now time to unveil what are the actual mathematical solutions of the circuit. And here they are. These two equations are the solution for the voltage and the current over time for this very simple circuit. As you can see, they are exponential, and exponential equations are usually the type of solution that you get when you have a capacitor and a resistor in your circuit. So it's really important to understand how they work. They might look a little bit intimidating, but actually they always have the same appearance, and it's kind of easy to understand which one it is and how to determine the different parameters. We won't go into detail into this lesson, but I want to give you a high-level understanding. Before proceeding further, I would just want to give you a little refresher on exponential functions, because exponential functions are everywhere in electronics, in particular in solution of RC circuits. So this graph that I took from the Wikipedia page, that I encourage you to use to get more knowledge and more to refresh your exponential functions. So let's say this is x and this is y. This graph is representing y is equal to e to the power of x. So now I want to highlight few characteristics of this function. So the first is that when x is equal to minus infinite, so we're going all the way down here, you can tell that y is going to be equal to 0. When x is equal to plus infinite, y is going to be equal to infinite. And then, very important, when x is equal to 0, y is equal to 1. E, I want to remind, is a Euler constant, and it's equal to about 2.72. Another thing that is very important is that This function never really reaches 0 here, so it keeps approaching 0, getting closer and closer and closer, but it will only get 0 really if you go to minus infinite. But anyway, it soon becomes very close to 0. And then the other thing you can note is that this function, after you move a little bit in the x-axis, it starts growing really fast. So that's another really important thing. Sometimes in the study of circuits, you will find, as we are actually already found in our case, a case where you have another function, and this function is gonna be equal to y is equal to e to the minus x. Because x is basically the horizontal axis here, you just replace x with minus x, so it's equivalent if you want to take the horizontal axis and flip it vertically. So what's gonna happen in this case is that the function will actually look like this. So it will be pretty much symmetric relative to 0, to x equal to 0, and that makes sense because if you think about it, now if you have x equals to infinite, it's equivalent to when you had minus infinite before, so you're gonna get 0. When you have x equals to minus infinite, now it's equivalent to have e to the infinite, so you get plus infinite, and again when x equal to 0, it doesn't make a difference, you always get 1. Now let's go ahead and study the solution here. So as we said, these one are the two solutions for voltage and the current in a capacitor. Those are the mathematical solution to this circuit, so they are perfectly exact. Let's look at the current one because it's slightly simpler, I would say. So this one, we see we have an exponential multiplied by a constant. So let's look at the constant first. So the constant is V bat, which is just a fancy name for the 10 volts of the supply. So it's the voltage of the battery, so it's 10 volt. Divided by the value of the resistor, 1 kilo. So this quantity in the parentheses is equal to 10 milliamp. So if you remember from the previous calculation, 10 milliamp is exactly the value that the current has at the beginning, at t equal to 0. So this point was 10 milliamp. This quantity is then multiplied by an exponential. So an exponential, we have just seen it before. We see that exponential is a type of exponential that has a negative horizontal axis, like in the exponent. The t is with a minus sign instead of a plus sign. So as you remember from before, the curve will tend to do something like this, where x equal to 0, we get 1. If this is x, in our case we have t, we don't have x, but exactly it's the same function, so it works exactly the same way. So you can see that for t equal to 0, the exponential function will be equal to 1, so it gives exactly this point here, exactly has a druid here, and it's also the same as the point that we found manually. And then, as you recall, as the time progresses toward infinite, the value of the exponent will slowly decrease, eventually approaching 0. So you can see that's exactly what we are doing with this function. So the quantity is decreasing, it's approaching 0, it never really fully reaches 0, but it becomes very close pretty quickly. Before moving on to the study of the voltage of the capacitor, let's study a little bit more the evolution of the current of the capacitor, because I wanted to introduce another important parameter, which is the time constant. By now, you should be familiar with the shape of exponential functions, and it should be easy to understand by studying the circuit what is the initial value of the current and what is the final value of the current. In order to draw exponential function correctly, you need to know 3 important parameters. So the first is the initial value of the exponential. The second is the final value. And the third is the time constant. The first point, the initial value, is easy to calculate, and usually it can be calculated by studying the circuit. In this case, if you remember, the battery is 10 volts. The initial value of the voltage on the capacitor is 0. So the moment in which you close the switch, the drop across the resistor will be 10 volts. Hence, we have a current here that is 10 milliamp. So that's the initial value of the current, easy to calculate. The final value is also easy because the capacitor, if the voltage is not alternating voltage, but it's just a constant voltage, after you close the switch, there will be a certain time for things to settle. but eventually the current has to be 0 in a capacitor. So we know that we are heading towards 0. So this is our point number 1 and this is point number 2. The question is now, what is the time constant and how do I calculate it? Well, the time constant is really important for exponential because it gives you an idea of the speed at which the exponential evolves. If you only have point 1 and point 2 and you have to draw an exponential, you are in trouble because there are infinite exponentials that you could represent. For example, here, an exponential that works with the initial value and the final value here could also look like this, or it could also look like this. So you could have a faster version or a slower version of the same exponential, and all of them will start at 10 milliamp and will trend towards 0 milliamp. So it's really important to know what is the speed of the exponential in order to draw the correct one, because there's really only one exponential that is the correct one. The time constant, fortunately, is easy to find. When you look at the equation of your exponential, you will always have the independent variable at exponent. That's what defines an exponential function. But usually you will also have some other numbers in it. Now this number could be multiplied to the independent variable, so it could be multiplying the t, or it could be a denominator, it doesn't matter. You can always take the exponential function and write it in a way that looks like this, where in the exponent you have a numerator, the independent variable, which is the time, and in the numerator you have a number. In this case, I use the Greek letter tau to represent the number. For example, if you have e to the minus t, that means tau is equal to 1. If you have e to the minus 2t, that simply means that tau is equal to 0.5. So you can always transform the exponential function to look like something like this. If you do that, whatever you collect the denominator, this is called time constant, and it is usually indicated with the Greek letter tau. Time constants are so called because the unit of measurement of the time constant is the unit of time, so it's second. In the case of this circuit, the time constant is equal to R multiplied by C. So if you multiply a resistance by a capacitance, you get ohm multiplied by farad, but that is also equivalent to seconds. For RC circuits, the time constant is always given by the product of an equivalent capacitance and an equivalent resistance. In this case, we only have two components, so the time constant could have only been R multiplied by C. How do you use the time constant to draw your exact exponential? Very simple. Here's what you do. So you already individuated in the graph your starting point and your ending point, the final value. So what you do is that you draw a line parallel to the time axis that reaches your final point. Like in this case, the final point is 0, so this line is basically overlapping with the time axis, but it doesn't have to be that case, it could be somewhere else, the final value. Now, from time 0, or for whatever was the time of your initial value, in our case is 0, you move along that line by the amount equal to the time constant. So in this case, we went from 0 to 10 milliseconds because 10 milliseconds is the time constant. So all you're doing that to find this point. Now you draw a line that connects your initial value to this point, and you basically individuate a triangle here. Now that you had the initial value, the final value, and you have this triangle here, it's very easy to draw the correct exponential. Actually, let me cancel this one so I can show you exactly how to do it. You obviously start at the initial value, no surprise here. And you know that eventually you're gonna trend to the final value. So now all you have to do is to determine the speed at which the exponential moves. And that's where the triangle comes into play. As you start drawing your exponential from the starting point, you have to make sure that the initial part of the exponential is tangent to the triangle. Once you do that, it will be very natural to draw the rest of the exponential in the correct way. So you start and you make sure that the two lines are tangent at the beginning, and then at some point you disconnect from the triangle and you just trend towards the final value. In most cases, when you apply a step voltage, like in this case, or a step current to an RC circuit, the circuit will respond with exponential waveforms. Drawing the exponential waveform of the current of the voltage does not require you to know the actual equations, but the only thing you need to know is the starting value of the voltage or current, the final value, and the time constant. Let's now move on to the voltage waveform represented by this equation. Again, to be able to draw or to recognize that the waveform is correct, we just have to individuate the three main points of the exponential curve, which is the starting point, the ending point, and the time constant. Let's start analyzing the waveform to see if it represents correctly the behavior of the voltage of the capacitor in the circuit. The starting point for the voltage was given by the problem itself, and that is something that you always need for a capacitor. It is usually a safe bet to assume 0 volts if the circuit has been sitting there without supply for a long time, but you cannot really tell for sure. So this was V equal to 0, and this was coming from the problem. So the first point was easy to find. The final point, it's also easy to find for capacitor. And again, if you have a circuit where your supply is just a constant like a battery, the switch is not continuously operated, open and close, but once it's closed, for example, it stays closed forever, and the components aren't changing value dynamically. So the circuit is just constant and let be, and you're just waiting for the voltages and current to settle. For a capacitor, you can always say that the current eventually, like after a very long time, got to be 0. And the voltage across the capacitor, it's also easy to find because once you know that the current is 0 in the circuit, you can easily apply the Kirchhoff law for the voltage and determine the voltage of the capacitor. For example, again, if you assume the current is 0, that also means the drop across the resistor here will be 0 because there's no current. And now, if you apply the Kirchhoff law, you will very easily determine that the voltage across the capacitor will have to be equal to 10 volts because no other drop is lost across the resistor or the switch. So that confirms that the final value here should indeed be 10 volts. The time constant is, for this capacitor, will always be the same. Doesn't matter if it's if you're talking about the current or if you're talking about the voltage, the time constant is the same, so it will be again RC. So just as before, what you would do is that you draw a line representing the arrival point, which is 10 volts, and you extend the line back to the beginning point, and then you, from the starting point, you measure a distance which is the tau. So this is the tau. Then you draw a line here, and then you make sure that your exponential at the beginning, when it leaves the starting point, it's tangent. And that's how you get the waveform for the voltage. As you can see, we actually determined the behavior of the voltage without looking at the equation. Now we can go back and verify that the equation is indeed presenting that curve. Let me delete a little bit of the curves here. So now, if we look at the equation, what we can see is that we have a constant term at first. So the constant term is equal to V bar. So this one is 10 volts. And then, instead of multiplied by an exponential, we have 1 minus an exponential. So that is always one of the two cases that you can encounter. So usually, when you have a behavior which is like the one of the current, so you start from a certain value and then you slowly trend exponentially to 0, then you're simply multiplying a constant by an exponential, a pure exponential. Whereas when you have the other possible behavior, which is you are trending up towards a certain value exponentially, similarly at the same speed at which you tend to 0, but you're just tending to 10 volts in this case. So usually the equation has that form. So you have the final value at which you tend, and then it's multiplied by 1 minus the exponential. And it's easy to verify that this works because when you substitute t equal to 0, then the exponential will be equal to 1. So 1 minus 1, 0. So the VC is equal to 0, which is exactly what we want. And then you can verify that when t is equal to infinite, the exponent of the exponential function will be minus infinite, so the value of this will become 0. So only the 1 will be left. So 1 multiplied by V bar is still V bar. So Vc is equal to 10 volt. So you see that it's correct, and infinite becomes 10 volt. The last thing that we have to verify is that the exponential is indeed using the right time constant, which is tau, which is Rc, which in this case is the only possible time constant that we have in this circuit. In the previous lesson, we have seen how to determine the main parameter of an exponential function representing the voltage and the current across a capacitor. As we've seen before, this waveform usually start at a certain point and then they slowly tend to kind of their final destination here, which is in this case 10 volts and 0 current. Now it's worth to highlight that mathematically those destination points are never really reached unless you really wait an infinite amount of time. So if you look at the mathematics, unless t becomes infinite, the value of the voltage will never be really 10 volts. In practical terms, you don't need to wait infinite because after a very short time, your voltage will actually be indistinguishable from 10 volts. So yes, technically it hasn't reached 10 volts yet, but there's no instruments on earth that will be able to tell you that you haven't reached 10 volts yet. To have an indication though of how fast the exponential waveform moves, that information is provided to you by the time constant. If you take two exponential waveforms and they have exactly the same starting point and ending point but different time constant, they will look very different. So this curve that we can call curve A has an equation represented by 10 milliamp multiplied by E minus t2 over 10 millisecond, right? So let's say now we represent another curve, a curve B. This curve B will also start at 10 milliamp, will end at 0, but now the time constant is 5 milliseconds, which means that either the resistor or the capacitor are smaller now. So in this case, if I go ahead and draw the waveform, I will have to do something like this. So again, I started at 0 time, and I move 0 is also the destination for the current. So I find 5 milliseconds here. I draw a kind of a straight line, and then I know that my exponential will be tangent at first, at least. So it will be something like this. So as you can see, this current will go towards 0 faster, and probably I didn't really do it really well here. It's probably more like this. Now I can remove this. And now if I wanted to draw another one that has 1 millisecond, then it will be even faster because the line will be here. So it will be like that. So it will be much faster, and so on. Same concept if I pick a time constant that is long. So the time constant in effect gives you an idea of how fast the exponential function moves. Up here on the top right, I have a table that gives you a better idea of that. In this case, we are looking at the voltage of the current, but it's the same concept. So the time constant gives you an idea of how fast the exponential function moves, and you can actually calculate after each of time constant how much percentage of the final value your voltage or current has reached. So in this case, with this little table, if we look at the voltage at time 0, Vc is 0, that was a starting point. So we have a 0% of Vc over V bar, knowing that the final value for Vc will be 10 volts, which is V bar. So initially we are at 0%. After one time constant, so that means at 10 milliseconds, we are at 63%. So one time constant is a very important time, because after one time constant, yes, we're still a long way to be exactly equal to the final value, but we are already 63% there. After two time constant, we are 87% there. And after three time constant, we are 95% there. So usually, like a rule of the thumb for like a circuit designer, is that when you have an RC type of behavior, you know voltage and current are evolving and exponential, it will take some time. You calculate the time constant, and then it is a fair assumption usually to assume that after three time constants, your voltage and current are pretty much at their final destination, meaning they are at their final values, meaning that they are like at 10 volts or 0 amp in this case. If you want it to be more accurate, you can even go more. You can use 4 time constant, and of course the more you add time constant, the closer and closer and closer you get to the final value. But as we've seen before, and as you can tell from the graph, the speed at which you move, the amount of percentage points that you gain for each additional time constant becomes smaller and smaller because you're approaching 100%. So you see with the 1 time constant you get 63% already. The second time constant already doesn't give you as much, but it gives you much less. It only brings you from 63 to 87. And then the third time constant only brings you from 87 to 95, and so on. And the next time constant can only give you up to 5% because you already have 5% and 95%. So usually a rule of thumb that I use is to assume that after 3 time constant, the voltage and the currents on a capacitor are pretty much at their final value. In this circuit, the time constant is equal to RC. So it makes sense that it depends on both resistor and capacitor. After all, this circuit is really very simple, and these two are the only 2 components we have. But I want to give you an understanding, intuitive feeling of why the product of those makes sense, rather than, let's say, the ratio or the difference or even just one of them. You can always represent RC circuit within a hydraulic example where the resistor is a constriction in the tube, and the capacitor is a tank, and the voltage in the capacitor is represented by the level of the water that you have inside. The current is the flow of the water into the capacitor, and then the voltage is also like the difference of pressure across the resistor. So this is the resistor and this is the capacitor. So now if you make the resistor twice as big, we know that for the same difference in pressure, so we have a P1 and P2, which for us really represent a voltage 1 and a voltage 2, where voltage 2 is the voltage of the capacitor. So for a certain difference of voltage, which is difference of pressure in this hydraulic example, if you make the resistor twice as big, you're gonna have a flow of water, which is a current, that is twice as small. So it makes sense that the tau is proportional depending on R, and the bigger is the R, the bigger is the tau, the slower the voltage will reach the final value. And at the same time, for the same resistance, so the same size of the tubes, of the pipes, if you have a bigger capacitor, so if the capacitor, let's say this tank, instead of being like this, is much wider, then in this case, for the same flow of water that comes into the capacitor, the level of the water will grow much slower, because now we have a bigger capacitor to fill, a bigger tank. So it also makes sense that the time constant is directly proportional to the capacitance for this reason. In the previous lessons, we have seen the charge of a capacitor from 0 volt to 10 volts through a resistor. Now we're going to look at what happens when the capacitor gets discharged, and we'll find out that the equations, the behavior is very similar, just slightly different. So we look at this circuit, we have a capacitor here with a certain starting voltage that we're going to set to 10 volts. So we assume this is a capacitor that's been charged at 10 volts somehow. And then we have a switch. Again, the switch is just used to determine a starting point for the discharge. And then we have a resistor of 1 kilo ohm. Again, the capacitor is also 10 micro, just as before. Before, of course, here we already have the solution actually, but even before we can look at them, you should immediately be able to tell a few things. So first of all, you'll be able to tell that whatever the voltage in the current will do, the way, the movement, the shape of the waveform will be exponential. Then you should be able to calculate immediately the starting point for the voltage and the current. Well, the voltage has been given, it has to be given, and the current is also very easy to calculate, because the moment the switch is closed, you're gonna basically apply these 10 volts across this resistor. So you have 10 milliamp, so the starting point for both current and voltage is defined. It's also easy to determine what is the final value for the voltage and the current. We know that the current has to be 0, so that's 1, that's easy. And then it's very easy to find out that if the current is indeed 0 at the end, the voltage across the resistor will be 0, and the resistor happens to be in parallel to the capacitor, so that is also the voltage of the capacitor. So both the capacitor and the resistor will be a 0 volt at the end. So there we go. Finally, the only thing you really need is the time constant. This is a very simple circuit. You only have a capacitor and a resistor, so the time constant is again equal to R multiplied by C. And there you have it. So the two equations, the two waveform will look like this. Now here, the two starting points, I'm representing the voltage and the current on the same graph just for convenience, which means that you have to imagine that the vertical axis, it's not unique, but you have two of them, one for the voltage, one for the current. So that's why these two waveforms don't overlap in this way. That is completely arbitrary. But for both of them, as you can see, I draw the little line here connected to the time constant, and then I use that to help me draw the exponential. And up here, I also indicated the formula that gives you the behavior of the voltage and the current. This time, because in both cases we're going from a value to 0, they both look the same. So you don't have the term that is 1 minus the exponential over tau, but you only have the exponential part. One of the most important applications for capacitors, in particular in modern digital electronics, is to be an energy storage for integrated circuits. When capacitors are used in this application for this role, they're usually referred to as decoupling capacitor. They're also sometimes referred as bypass capacitors. And what they do is pretty much to store energy, like any other capacitor, and then release it when the chip's needed. We'll see later why this is required. And pretty much the overall behavior of bypass or decoupling capacitor is that they behave like a local and faster power supply for the integrated circuits. Finally, capacitors can also be used to filter high frequency noise. On the right, I represented a simple circuit as an example to study the role of bypass capacitors. Here we have an integrated circuit, IC, usually present themselves in boards as a little black boxes with many pins. So in this case, I imagine that this IC has two pins dedicated as inputs, single, and one pin dedicated as an output. So we don't know exactly what this IC does. It's not important for this explanation. You can imagine that maybe it takes input 1 and input 2, sum them, and provide the output at the output pin. Other two pins that you're going to find on any integrated circuits are the ground and the power supply. So these are the two pins that you have to use to connect the chip to a power supply source to a certain voltage. And these are obviously required in order for the chip to work. Without a power supply, the chip won't be able to work. Now, ground is usually indicated with G and D, so it's pretty self-explanatory. While the supply, it's usually called VDD, it could also be called VCC. Very often the case that more than one pin is dedicated for ground and for VDD. These two pins are obviously going to be connected to a battery eventually, which is always what we imagine as the power source for the circuit. So the battery is here. And with this two little symbol, I wanted to indicate that the battery is not necessarily sitting next to the chip. It might be really far, it might be quite a big board, and the battery might be located on the other side of the board. So there might be quite a distance, and the trace that connect the battery to the chip might be pretty long. Just by looking at this little circuit, I can tell you almost immediately that this circuit will never work. Even if I don't know what is the IC doing, even if I don't know what kind of IC it is, I can already tell you that this circuit has a very high chance of not working. The reason for it is that it doesn't have any bypass or decoupling capacitor. If you take any data sheet of any IC, whether the IC is analog, whether it's digital, you will almost always find a request for a bypass capacitor. So a bypass capacitor will be represented in this schematic like this. So a capacitor between the power supply and the ground. Usually the datasheet will also tell you that this capacitor not only has to be connected like this, but it should also be located as close as possible to the pin of the integrated circuit. So sometimes these VDD and ground pins are located very close to each other in the symbol of the schematic, so that you can clearly show that the capacitor is going to be next to it. Sometimes you don't indicate the capacitor like this, connecting it between the two sides, but you might write something like this. You might just do like this. So you have a capacitor and then you indicate that it's connected to ground, but this way it's kind of obvious that this capacitor is really sort of belong to this component. It's really next to it. In order to understand how this circuit works, let's start describing the role of each of the actors. So the first is the voltage generator, or the battery. As we know, this is, as the name implies, generating a certain voltage. It could be 3.3 volts, for example. And apparently, because of the way we connected the circuit, this is the voltage that is required by the chip. Different chips require different voltages. Another thing that should be intuitive is the chip. The integrated circuit contains other little circuits inside. They're fabricated in a different way than normal other components, but nonetheless, you're gonna have resistors inside, capacitors, and so on. So, in order to execute this function and to do whatever it's supposed to do, it's gonna require a certain current as well. So, as the chip is working, not only it will see a certain voltage at its terminal, so from here to there, you're gonna have exactly the same voltage V. It's also going to require a certain current in order to operate. And the same current will come in the supply, will come out of the ground, and then it will return to the battery. In order for you to understand why bypass capacitors are needed, I need to tell you a little bit more about the waveform of the current going in and out of an integrated circuit. Now you might be thinking that the current would probably look like something like this. A constant current over time. Why not? After all, integrated circuits do like constant voltage over time. So it seems natural that they might also like to have a constant current as well. Well, in most of the cases, 99% of the cases, the real waveform of the current in an integrated circuit looks much more like this one. In particular, when we are talking about digital chips. Why that's the case? Well, let me give you a little example that should be easy to understand, something you are certainly familiar with. Let's consider your computer. When you bought your computer, the most important chip in your computer is the CPU, the central processing unit. And nowadays, CPUs are ranked by number of cores, but one other important parameter is the speed of the clock. So the clock is a timer for the integrated circuit that is used to organize the different operations inside the CPU across time. So the CPU is really complicated. It has many circuits that has to work together. So if you don't give them a little bit of order, nothing will get done. So you need to organize them and make sure that operations are executed in a timely manner. So what happens is that the CPU usually have a pin where you have to apply a clock. A clock signal is a clock that looks like this. A series of pulses, this is voltage, a series of pulses that keeps repeating themselves forever. And they have a certain period, which is indicated with T. And the frequency, that is usually what is quoted for the CPU, is the inverse of the period. Now, these pulses are used to synchronize the operation inside the CPU. So every time there is a pulse, let's say, we could be on the rising edge of the pulse, like there, a bunch of operations are executed. And when the operations are done, no operation is executed until the next rising edge, for example. Operations inside the CPU are what requires a current. So if the CPU is sitting idle and not doing anything, you can assume that the current that will require will be really low. And that is the case. Most of the current is required when operation needs to be executed, because that's when things move inside the CPU. So if you want to represent the current in this graph, I'm going to use the red now. Most likely the current will look like something like this. It will be low here, and then it will have a spike here. Then it will be low, it will have a spike. Low again, and then it will have a spike. Another reason why the required current might not be constant is simply because the user might suddenly change what it's doing with the computer, and so all of a sudden more current might be required. For example, you might be one moment you might just be staring at your desktop, so not really much is going on, so probably a little current is needed, and the next moment you might be running a 3D video game that instead requires a lot of computing power. So that is why most likely the current for CPUs and for integrated circuit looks much more like something like this. Now, the average current that is required might very well be very similar to the example above, to the constant value of the current. But the actual waveform is completely different. It has a lot of spike and burst and up and downs. And that is why, as we'll see soon, you need to have bypass capacitor in order to guarantee a constant voltage at your device. Before I turn to the electrical circuit, I want to give you another water analogy to help you understand better the role of bypass capacitor in circuits. So I'm going to do that using this sort of a hydraulic system where there is a sink and the faucet. and this faucet has a knob, and then this faucet is connected to a pump using a very long pipe. And down here we have a cistern or maybe a well where there's a lot of water and the pressure is pretty much constant. So the idea here is that you have this well where the pressure is, let's say the pressure is 0, and then you have a pump that generates a certain pressure P, and now the water is pressurized at this pressure available for you to use. So the moment you open the knob, the knob is pretty much representing a resistance in our circuit. So the resistance could be infinite if the knob is closed, which means there's no current, which means there's no water coming out. But the moment that you open the knob, you're going to set a certain value of the resistance. Here you have 0 pressure. So the difference in pressure is delta P divided by the resistance. It will give you a certain flow of water. So you get a certain I, a certain current, which is your water stream. To understand the effect that all of these operation on the knob have on the pressure, we have to look at these more closely in the time domain. So let's have a little graph here with the time in the time domain, and let's assume that the knob is operated in this way. So the knob is kind of closed at the beginning, then at some point it is open, and then eventually it's closed again. Now let's look at what happened at the pressure. So this hydraulic system has been designed to have a constant pressure of P before the knob. That was the design of it. So we know that we start with the pressure equal to P here. Pressure is equal to P all the way till the moment in which the faucet is open. Now we know that because the pump will do anything in its power to get the pressure equal to P, we know that eventually the pressure will return to P after we open the knob. And we also know that the pressure will return again to P after we close the knob. What we really want to know now is what happens a short amount of time after the knob has been opened and after the knob has been closed. So you might be tempted to think that the pressure will still be equal to P, because after all we have a pump and the sole goal of the pump is to keep the pressure constant. However, think about it in physical terms. So if this is really an hydraulic system with a very long plumbing, the moment you open the knob, a large amount of water will be allowed to exit the faucet. Remember that the pressure is a representation of the presence of a large amount of water into a tight space. The moment you allow the water to exit your faucet, all of a sudden your pressure has to decrease because there's just less water available to generate that pressure. So as a consequence, the moment in which you open your knob, the pressure will suddenly drop, and later it will recover thanks to the action of the pump. At the same time, the moment in which you suddenly close the knob, the pressure will suddenly increase and then will decrease, returning to the value established by the pump. What we're saying here is that the pump, it takes some time to realize that the pressure has decreased, and it will try to increase the pressure at the faucet by injecting a higher amount of water into the system. But in order to do so, and it's because we assume the tubes are really long, it just takes some time. So the very moment you open the knob, you open the faucet to get more water, the pressure will suddenly decrease to then recover to the original value. So what can you do to improve this system? What if you don't like that the pressure has a sudden drop or a sudden overshoot? You want to keep the pressure as constant as possible. Well, what you can do is that you can add a pressure tank to the system. So this that I'm representing here is a pressure tank. So it's a device that is filled with water at a constant pressure and is connected very close to your sink, to the faucet of your sink. So now, when you are applying a certain pressure P, here you have pressure equal to P everywhere. This pressure tank is obviously representing a capacitor. So as you can see, because we have a pressure P here and pressure 0 here, we have the elastic membrane that has been bent, as we've seen in the past, and some energy is being stored into the capacitor as elastic energy. If you think about this situation as a steady state, everything works just as before. You have a certain amount of water coming down. Now let's go again and see what happens when we suddenly open or close the faucet. In time domain, that's what we do again to the faucet. We just open and close it really fast. Well, just as before, the pressure was P before the knob, and all the way through it will be P again eventually, and it will also be P here. The moment in which we open the faucet really fast, we see that the amount of water available before the knob will just decrease. That will generate a sudden decrease of pressure. However, in this case, if the pressure P decreases, so if you have now something that is smaller than P, that means that the capacitor, the membrane of the capacitor will suddenly be able to push a certain amount of water up in the stream. So a certain amount of water will be provided by the capacitor, because now the steady state equilibrium of the membrane is not respected anymore. The membrane is actually able to go up a little bit because the pressure has decreased. Hence, some water will be injected in the system. The net effect of this is that you will still have a drop in the pressure at the faucet, that is inevitable, but the amount of drop at the faucet will be much smaller than before. And the same can be said as far as when you close the faucet, the amount of overshoot of the pressure will be much smaller now. The simple reason for that is that you have a storage of energy, in this case pressurized water, sitting very close now to your sink, and the moment the pressure decreases at your sink, at your faucet for any reason, this device will automatically inject or take in an additional amount of water, trying to compensate and to keep the pressure as constant as possible. Naturally, unless you have an incredibly fast device, incredibly fast pressure tank, you're always going to have a certain delay in which this additional water is provided. But at least if you have a lot of this pressure tank next to your faucet, the amount of pressure drop that you will feel will be much smaller, and probably you wouldn't even be able to feel it at all. If that wasn't obvious enough, let me now state or reveal that the sink and the faucet in this hydraulic circuit represent the integrated circuit. So this is the user, this is the device that is responsible for requesting this kind of currents that go up and down. The pressure tank is the bypass capacitor, and a pump is representing the voltage generator or the battery. Now it should be much easier to understand why bypass capacitors are fundamental components in electronic and fundamental companion of any integrated IC. Integrated circuits, they require a constant voltage in order to work. The voltage doesn't need to be perfectly constant, but it needs to be within a certain tolerance band. So for example, if your nominal voltage is 3.3, you can allow the voltage to go as high as 3.5 or as low as 3.1, but you don't want to go beyond this range. If the voltage is too high, you risk to break the chip. If it's too low, you risk to turn it off. Unfortunately, integrated circuit likes to require currents that behave like this, that jumps up and down really fast. And that makes it very difficult, if not impossible, for the battery to provide the current and to guarantee that the voltage always stays within the tolerance band. In the context of the hydraulic circuit, we said that that's the case because the water needs some time to replenish the water that was consumed at the faucet. In this case, the real explanation involves also the concept of inductance, but you can still think it in the same term. The charge needs some time to go from the battery to the device, and if the device, the integrated circuit, changes the request of current immediately, it will take some time for the power supply to provide the additional current required. So the presence of the capacitor as an energy storage, as a charge storage, if you will, next to the integrated circuit can be very important because it can supply the additional charge that is required in moments of needs. So if we look at this current and we assume that is the current that is requested by an integrated circuit, if you didn't have a capacitor, so you will start from the nominal, let's say this 3.3 volts. So you start until the point, and then when you get here, you will get a drop, a quite significant drop. Then the voltage will slowly try to recover thanks to the voltage generated to the battery. But then again, it will be hit one more time by a very strong current. Then it will try to recover again, and then it will be hit again. Then it will recover here and hit once more. And then finally, maybe he will allow to actually return to the final value because there's no more current anymore. And so the voltage supply can provide the charge required to bring the voltage at the integrated circuit back to the nominal value. With a bypass capacitor, the impact on the voltage, it's much smaller. It's probably gonna look like something like this. So when there is an extra current that is required, you are gonna be hit, but the amount of drop of the voltage is gonna be much smaller, and then the system will recover. and so on. So here it will be hit again, and here the release will look like that. So here will be hit like this and like that, and here it will do something like this. So you can see here the voltage still changing due to the erratic, if you want, behavior of the integrated circuit, but thanks to the presence of the bypass capacitor, the change in voltage is much smaller, much more contained. Another very useful application of capacitor is filtering. Filtering is an operation where you have an input signal, a certain voltage waveform, you pass it through a filter, and as a result you have another version of the same signal out, which supposedly remove part of the signal that is not desired. The part of the signal that you might want to eliminate could be straight up noise. That's definitely something you always want to remove. But it could also be part of the actual signal that you just don't need, or that just will make things more complicated down the line. Now it's kind of hard to understand, but to give you sort of an idea of this, think about MP3 files. So when you take a song and you convert it to MP3, you are losing something. And you're losing useful information because it's removing some of the frequency that are part of the audible range for humans. But what you get out of it at the end is something that it sounds very, very similar to the original song, but it occupies much less space on your drive. So it's a trade-off that is worth making in that case. And with filtering on circuits, it's the same story. Most of the time the filtering is done to remove noise, but sometimes you just have to kind of reduce the spectrum of your signal to make it easier to be digested for other blocks down the line. Now here I have a little example of a circuit made with the RC components, so a resistor and a capacitor. So this filter is usually called, it's a low pass filter, and we'll see what that means. And let's just look at what happens at the output if we apply the input waveform that I indicated in red. So the input waveform is a voltage. I use this kind of strange symbol to indicate that it's not a battery, but it's a generator that can make any waveform you want. And then we have a resistor, capacitor, and the voltage across the capacitor is the output of this filter. So if you want, the block that I indicated below, the filter that I indicated below, will be this guy here. So we just want to see how the V out in blue looks like given the input signal V in. In order to be able to solve the circuit, I need to give you some information related to the components. I don't need to give you the values of the components, but the only thing I need to give you is really the time constant, the product of them, as you should remember from the charge and discharge lesson. So the time constant is RC and has a unit measurement of time. So we can compare the time constant dimension relative to the graph here, and depending on that you're gonna get very, very different results. For example, let's say one time constant, 1 tau, is this size here compared to the time scale. Now this is a very short time constant, so the output of the circuit will look like something like this. 3 time constant, 3 taus, will make the capacitor basically reach the final value of the input voltage. So we'll start from 0, let's say, and now in about 3 time constant, this will reach up here, then we'll do down here, almost all the way up, down, the final version of the voltage, the output voltage, resembles the input voltage. So you can tell that this is sort of a filtered version of the input, but all the hard edges have been removed. And that is why this filter is called low pass filter, because it only allows the low frequency components, so the components that move very slowly, to pass through, whereas the fast components are attenuated. If you recall, a capacitor doesn't like to change its voltage, so in order to change its voltage you need to apply a lot of current. So as a result, if you apply voltage to a resistor on a capacitor in this configuration, what you're gonna get is that the low speed moving components will pass through in the output signal, whereas anything that moves really fast will be attenuated. The first step here was being smoothed out but rounded a little bit but you have the whole intensity is there, so the voltage actually reaches the peak. While this little pulse that is really, really fast, up and down just really fast, you still get something out, but it's attenuated. The peak is much lower now. So the output signal now, the components that want to move really fast have been removed.